to share my lecture, especially on the research that we did in USM. So the title is the controlled growth of bismuth ferrite with enhanced photocatalytic performance towards pollutants degradation. And I hope that everyone will be benefit with this sharing. Okay, so first of all, my research area is more towards the environmental catalysis. Okay, so as we know that there's a lots of environment problems, yeah, so we need to find solutions, especially on the conversions of wastewater towards a treated water. So we really need a new generations of, maybe it can be an adsorbent, it can be a membrane, it can be a photocatalyst as well. So all of it have their own benefits. Okay, so for the adsorbents, is actually an adsorption process, okay, where the pollutants adsorb on the solid surface, while the membrane, it can act as a separations barriers, filters or sieve to specific size of contaminants before it can convert into a clean water. While for the photocatalyst that we're interested to look into, known as the heterogeneous photocat, is about an adsorption. The process is all about the adsorptions of photon to produce the hydroxyl radicals and also a super oxide anions, okay, before it can convert all the pollutants into a simple mineral, carbon dioxide and water. Okay, usually we use a semiconductor materials, okay, such as metal oxides, perovskite, and so on. So all of those, okay, we need to ensure that it needs to have a high efficiencies, relatively low cost, small footprint, and also easy to operate. All right, so I zoom in into a heterogeneous photocatalysis. Okay, so basically we have a geometry of structure of the metal, where we have the metal nanoparticles, we have a metal nanocrystals and metal atoms. So the structure as well as the size is different, okay, as well as the electronic structures. For the metal nanoparticles is on the metal energy band, for nanocrystals is on the molecular orbitals, and atoms is on atomic orbitals. So we want to look at these particular parts, which the metal nanoparticles. And as far as we're concerned, I know that everyone knows that there's a lot of method that we can fabricate these metal nanoparticles to be one of the photocatalysis. So it can be a top-down from bulk into nanostructures, or it can be from bottom-up approach, from atoms into clusters, and the end product is the nanostructures. But what is all about of the nanostructures, what we control, okay, is actually about this crystallizations. Okay, so if you can see here, this is actually a crystallization pathway. So this is the pathway A, and then this is a pathway B. Okay, crystallizations is actually kinetic control, is one of the conceptual as a progressive modifications of the activation's energy barrier of nucleations and growth, okay, before you can produce a product, final mineral. Okay, so this is for the pathway A, you can see this is a one-step route to the final mineral phase. Okay, but if you look at the pathway B, okay, it will depend on the free energy of the activations of the materials, and then and associate with the nucleations, growth, and the phase transformations before it can comes into the final product, which is the final material that we want. All right, so all of this is actually under thermodynamics and kinetic control. So when we understand this, okay, so we will look into what is the synthesis method. So for today, I would like to share of one of the materials that we done in the lab, which is bismuth ferrite, one of the perovskite structure that having a very good narrow band gap, okay, to be response to the light, so that it can be response into a visible region. Okay, but there's a lot of methods involved actually by previous researchers, okay, like sol gel, hydrothermal, microwave, electrospinning technique, and so on. It depends on different conditions as well. One can be with calcinations, without calcinations or annealing, and it will affect the grain size of particles as well as the morphology. But what the researchers come across all this while, they always having a difficulty to produce a pure bismuth ferrite structure. Usually they will comes with these impurities, okay, that will impact on the low photocatalytic activity. And some of it, most of the synthesis methods, somehow it can be impractical and also expensive, and also need usage of high concentrations of mineralizers such as sodium hydroxide, potassium hydroxide, and somehow it needs a longer time and also poor reproducibility. So in our research team, okay, we try to having this approach. We call it as a biotemplating that can control the growth of the nanoparticles that have been produced. So it starts with the work in Bristol. Okay, there's a, if you can see this in 2010, there will be the magnetic leaf. Okay, this is the leaf that been used as a simple skeleton and also templates for the iron carbide, and it is magnetic. This leaf is magnetic. And then there will also a self-supporting superconducting that replicates as a pasta shape here. Okay, that's yielding a product with 3D architecture. So biotemplating is about the interactions between organic and inorganic phases that we can explore what happened when soft meet hard materials. Okay, there's a lot of polymer templates, okay, that we can use, such as neutral polysaccharides, cationic polysaccharides, like chitosan. For neutral polysaccharide, we can use cellulose. Anionic polysaccharide, we can use algae. Polyphenols, we can use lignin, and also polypeptides, that maybe gelatin, that we can use to be a template for our productions of nanomaterials. Okay, so what happened here? When you want to control growth of the material, it depends on several factors. Okay, so for example, here, this is the basic concept. All right, when you have a biopolymer gel that containing the metal oxide, any metal oxide that you want to produce, all right, the acetate salts, then you introduce it to heat, okay, it starts to having a nucleation of the intermediate oxide nanoparticles, okay. Further, into heat or air, it will become an oxide. If you expose it into heat and also nitrogen's flow, it will become a nitrite, okay? If this is really nitrogen-rich gel. But if you just heat it with the flow of a little bit nitrogen, it can be a carbide. So it depends on the conditions, right? So for this biotemplate, as simple that I can show you that the advantage of this is from the biopolymer or ready-made natural templates into a nano microstructure metal oxide from nature to lab. Okay, so the advantage that using this synthesis, we can control the hydrolysis, the polycondensations, the nucleations and growth of the metal oxides, okay, in terms of its size, morphology, porosity, and the composition, okay? And then it also have the ability to generate a homogeneous and correct complex metal oxides crystal phase, okay? And we understand that when we use a biopolymers, okay, so there will be a lot of different functional group, depends on what kind of biopolymers that we use. All right, so this functional group of polysaccharides or biopolymers that we use can be a preferential chelation site for controlling the material at the nanoscale level. When everything is done, so that we can use that particular material as a potential for adsorptions and the removal of pollutants. All right, so this is like a mechanistics diagram about the metal oxides and the polysaccharides as an efficient hybrid associations for material chemistry. You can see that lots of preferential site here for alginates, especially. Okay, it can trap cation. Okay, and then cellulose having a lot of hydroxyl group and hyaluronates as well. Okay. So what is happening actually? The mechanism. Okay. From this schematic diagram, you can see it represents the possible interactions between functions of the polysaccharides units here, all right, and also the metal containing species. Okay, so most of the interactions, it can be a complexation, it can be a solvations, it also can be the hydrogen bonding, and most of it depends on the functional groups of the polymers or biopolymers that we use, as well as the experimental procedure such as pH, concentrations, and temperature. Okay, that is the basics concepts of how we can control the growth. Okay, so today I would like to share with you just two examples of the polysaccharides that we use, or it also known as the hydrocolloids. Okay, so what is hydrocolloids actually? It's a polysaccharides of high molecular weight extracted from plants or algae, or it can be produced by microbial synthesis. Okay, these hydrocolloids, okay, having a hydrophilic properties in nature because it contains a large number of hydroxyl groups that arrange along the backbones of the molecule. Okay, we will look at it further later. So from this hydroxyl group, these hydrocolloids having a sequestering ability, okay, so that it can allow the chelations of cations, either in mono, divalence, or trivalence, okay, and the cross-linking of the hydrocolloid chains will form a complex macrostructure before it turns into a desired product that we want. So, while having this sequestering ability, it will undergo a gelations, right? Gelations in the hydrocolloids occurs preferred by the intra and intermolecular hydrogen bonding that comes from most of the functional group. Okay, so in the gel state, the hydrocolloids form will extend as a network of complex entangles molecules. So the formations of these helical regions will provide higher order structure for the templating purposes of any metal that you want. Okay, so there's several examples of the hydrocolloids. It can be from the red algae, it can be alginates from the brown algae, Carrageenan red seaweeds, okay, gelatins, gum arabic, locust bean, and so on. So this is all a list of common hydrocolloids. Okay, so this is the examples. This is the alginate, comes from the algae, and then this is the Carrageenans from the red seaweed. Okay, this is gum arabic and also locust bean gum. So today I would like to concentrate on those two, alginate and Carrageenan only. Okay, so first we go for a Carrageenan. Okay, this is the red seaweed. It's a polysaccharide derived from the family of red seaweeds. Okay, there's a lots of types. One is kappa, iota, and also lambda. But usually, for templating purposes, okay, we always use kappa carrageenans because it consists of the repeating disaccharides units of alternating alpha digalactose as well as the beta and hydrodigalactose residues, okay, that join in a linear chain, right? So those functional group here, okay, it can sequestrate of discrete metal cations that can provide the basis for nucleations and also growth of the nanoparticle. So what is the methods of bindings? The cations actually will bind with the sulfate group here, so that it can tying the helices together, and then this will result of these cation mediated interactions, and there will be a formations of a stronger contracted gel when it starts to interact, when it starts to bind together. All right. So basically, you will have this precursor, any salts that you want, all right, and then the hydrocolloids, okay. So when the gelations or chelations occur here at particular pH, so that this is the optimum conditions that I show, all right, pH 10 at 2 hours, okay, we stir it at overnight at 80 degrees C, and then before we calcine for 2 hours at 550, okay, to sacrifice all the templates. So what happens here? When you're having a gelations process here, okay, this kappa carrageenan, this is your precursor, all right? So kappa carrageenan will build a cage, okay, they're acting as a nano reactor, okay, to coordinate the cations to the hydroxyl groups and promote cross-linking to protect and stabilize the metal oxide nanoparticles before it can undergo a calcination process. Okay, so this is the products obtained, where we found the bismuth ferrite with the particle size of 97 nanometers with a band gap of 2.07 electron volt. And you can see as well as a D spacing of 110 HKL from the TEM image. Okay, so this is what happened. Right, so we can see that it is at pH 10, right? So what happened here, as the pH value increase, okay, kappa carrageenan will self-cap the bismuth ferrite, okay, while within the superstructure, the iron 3+, okay, will start to detach from the kappa carrageenan and sulfate to migrate towards the particles nucleation sites here. So when they having these nucleation sites, the cross-link chains will assemble as a protective layer. It will arrange themselves like this, okay, and stabilize the form of the particles inside, okay, in a basic solutions, okay. So these localized area becoming the growth sites, and then when the calcinations process occur, it will eliminate all these organics materials of the kappa carrageenan and remain the structure of the bismuth ferrite nanoparticles. All right, so you can see from the FTIR, okay, the functional groups of the kappa carrageenan can be observed in the region 4 here. Okay, here 1283, 1078, and 936. It comes or corresponds to the ester sulfate stretchings that comes from the glycosidic linkage of the kappa carrageenan backbone. But after calcinations, you can see there will be no or disappearance of this backbone anymore. Okay, and the new peak exists at region 5 here. Okay, the formations of the metal oxide interactions, right? So there will be several effects or several parameters that need to be concerned. Okay, first it may be from a temperature. Okay, so this is the FISM image. Okay, at pH 10, all right, with uncalcined samples and the calcinated samples. Okay, so the calcination temperature having a profound impact on the morphologies and also kinetic crystallizations. Okay, you can see here the irregular structure, and it is in a very bulk sizes. Okay, when the precursor will the precursor is uncalcined, but when you start to calcine it at 500 degrees C, you can see the morphology turns into like a morning glory like, all right? And then for 550 degree, you can see a cubic structure here form. And if you further increase the temperature to 600, all right, it can change, change and elongated into rod structure. So the temperature will be really impacts on the kinetic crystallizations process. Okay, so there'll be another effect of how many or what is the best concentrations, okay, of the biopolymer that we should put. So we try to put like 0.5, 1%, and also 2%. So you can see from the FISM, there will be a difference in the particle sizes. Okay, so what we found for sample 0.5 degree is a sample 0.5% of carrageenans, okay, as a biotemplate. The particle size is quite large, it's about 1 micron here, okay, but when we put 1% and 2%, the particle size starts to reduce to 96 nanometers, as well as the crystallite size here, okay. It's also affect the band gap. All right, and then to simplify it, the optimum concentrations of this biopolymers used, all right, may contribute to the higher nucleations rates and faster nucleations formations of the crystal metal oxide with smaller crystallite size. Okay, and then it's also reflects the XRD, where you can see the broadening of the peak. Okay, so from here to here, you can see a broadening of 110 peak, right? The main peak here, okay, that correspond to the reductions of the crystallite size, right? So high concentrations of the carrageenan is actually reduce the volatilizations of the bismuth cations, okay, and it also can maintain the homogeneous stoichiometry distributions for the crystallization, okay. That's about the carrageenan. Now I move into alginate. Okay, alginate is actually another algae. Okay, it looks like green, like at the back. It's unbranched, still linear chain, but this is the anionic polysaccharides. Okay, that consists of the polyglucuronate G and a polymanuronic M, and the alternating GM, right, residues. Okay, so these poly G blocks, okay, this particular poly G block, right, having the ability to bind the cation strongly. When two poly G regions, okay, on the separate alginate molecules align together, okay, like here, okay, right, a pocket is created, okay, in which the cross-linking can occur readily that sequester the metal ions. All right, so again, it's simple. The procedure is like this: precursor as well as the hydrocolloids, the gelations or chelating process before calcinations. Okay, what happened for alginate? All right, so you have the G block here, right? Okay, so this G block can be a preferential site for the uptake of the metal cations, okay? So we call it as a poly G egg box, this egg box, okay? These egg box leading to control the nucleations and growth of the nanoparticles. There's also be a cocooning effect that prevents the coalescence, and it can enhance the homogeneity of the dispersed nanoparticles. And this is the obtained product. You can see that the particle size is about, by using alginate, the particle size is about 87 nanometers, all right? And you can also see the 110 reflections of the displacing here, all right? Okay. So we see the effect of the temperature, okay, from the SEM image. This is 550, 600, and 650. Okay, there's a changings of the kinetics, yeah, of the grain grown, while higher temperature will correlate it with the existence of the secondary phase. When it turns into rod particle like this, definitely in XRD we can observe the secondary phase of the bismuth ferrites. Okay. And the effects of the bismuth and iron ratio as well, okay, that's strongly depending on the competitions between the nucleations and crystal growth by the compositions of the precursor, okay. So if you can see that the molar ratios of the bismuth and iron here, this is 1:1, this is 1:2, bismuth 1, iron 2, and then this is 1:3, this is 2:1, bismuth 2 and iron 1. So it will impact on the morphology light. So first is like a bamboo light, then you can get a rhombohedral with the perfect ratio, okay. If you increase the iron, it starts to agglomerate, and if you increase the bismuth ratio, it starts to convert into a spherical nanorows like this, okay. So it depends on that, okay. And it's also having an effect of the concentrations of alginate, okay, again, from 0, 0.5, 1.5 to 2, okay. So on this, okay, there will be a carboxylate active sites, okay, of carboxylate group here and also the hydroxy group here. Form intra and intermolecular ionic and hydrogen bond for the crystallizations to occur, okay. But if you start to increase more than 1%, all right, so there will be too many preferential sites for the nucleations and growth of the metal cations, so it will reduce the preventions of the coalescence of the nanoparticles. So all those preferential sites will clump in together, all right, and then it will reduce the preventions of the aggregation. So it's not stable anymore. That is because you can see most of it is not, it's a big clump like this, okay. And then there will be also effect of pH, okay, for this alginate. You can see that this is for the unadjusted pH, all right. So you will get a cubic structure. When you start to increase to pH 4, it happens to having a needle-like structure. This is just a matter of the nucleations starts to occur. And at pH 8, the best that we can get a rhombohedral structure here. When we start to having more higher pH, all right, to pH 10, the particular materials morphology is not so good and quite be irregular with this fiber light, okay, because you can see a bundle of smaller filaments like this due to the highly anisotropic biopolymer at low pH, okay. And then at really high pH, you can see the abnormal grain growth, okay, due to high content of hydroxyl group in the equilibrium that contributes to larger and defect surface formation, okay. So that is most of the control growth of the bismuth ferrite that we did in the lab, okay, and then we can move into the performance, okay. So after we get that, okay, we try to see the performance or effectiveness towards various of contaminants like neutral red, methyl orange, offload saxine, methylene blue, as well as the phenol molecules. Okay, so again, it comes from this concept. Okay, we have that photocatalyst. Okay, by using direct sunlight. Okay, so this is the mechanism that been done. All right, so okay, this is a recent one where this is absolutely just on alginate, okay? So you can see alginate template can be the photocatalyst for methylene blue, neutral red, but not for methyl orange, okay? So you can see a removal of those, okay, but it's not for methyl orange. So we need to modify that, okay? There'll be a future work on this. Okay, so but from this you can see there will be several particle sizes that you can see by controlling the basic parameters that I already show you previously. Okay, and then it's a factor percentage removal of the various dye as well. Okay, and then we try to see the comparative study of the solar phantom, okay, by pure and impure biotemplate bismuth ferrite photocatalyst towards 4-chlorophenol. So what we found here, it's both of the materials having a degradations towards efficient degradations toward 4-chlorophenol, but when we compare it, okay, we can see that in that condition, it's not really good because there's no photocatalytic properties that appear, okay? The absorption is not so good. And then we change the pH, the control of the concentrations of the pollutants using the concentrations of hydrogen peroxides, the dosage, and so on. So what we found most of the pure bismuth ferrites having a remarkable degradation percentage over the impure bismuth ferrite. Okay, so for this work, the kinetic study, it's under a pseudo first order. Okay, and then we move to another study where we try to dope with the yttrium. Okay, for this particular study, we try to see whether it can degrade the methylene blue. Okay, so when we try to having a dopant here, all right, the magnetic properties also improve, and the performance also, you can see here, it's obey a Langmuir-Hinshelwood kinetic model, but from all of it, 1% yttrium dope will be the most efficient towards the methylene blue degradations. Okay, so for undope is about 87 within 120 minutes, but when you start to add 1% of yttrium, it starts to increase about 92.6%, right? Okay, and then after we have that particular materials that work, okay, so we try to embed with the biomass to support the SDG, okay, about the sustainability products. So this is the natural rubber waste. This is the collaboration work with the UKM, okay, where we convert it into the heterostructures of the bismuth with LNR, okay, and it becomes as this foamy adsorbents, okay, but these adsorbents having the particular bismuth ferrite photocatalyst, and it can react really good towards direct sunlight, okay, rather than just adsorb the pollutants. It can create that conversions of pollutants into an intermediates and finally towards water, carbon dioxide and simple molecules. Okay, so for this study, we can see that there's a lot of open pore structure with high surface area, so that it can ensure that we will have more active sites. Okay, so this is the degradations results. Okay, so we can see it works really good, about 94% under direct sunlight. Okay, and this is the scavenging materials, okay, for EDTA, isopropanol, ascorbic acid. So these materials are needed, this test needed to ensure that which particular mechanisms that really happen in the degradations. Is it just for superoxide radicals, or is it for the hydroxyl radicals, and so on? Okay. And then this is for the liquid natural rubber. Okay, so another work with technological industry from USM as well. This is the cellulose material. Okay, so from that we can see from this biomass of the waste materials, we convert it into a carboxymethyl cellulose, okay, CMC with the hydrophilic structure, okay, to ensure that we can having a good absorptions of dyes before it can react. The active sites of the bismuth ferrite on top of the cellulose can react with the photon and do their works. Okay, so what we can see that by only CMC and CMC bismuth ferrite here, okay, there will be a removal efficiency with not really, because this is really dark conditions, okay, but once you have to propose it into the sunlight, so it gives you the good results like this, okay. So within 120 minutes, you can see that by CMC bismuth ferrites composite, there will be a good degradations, okay. And then this is most of it, the kinetics is on the pseudo second order. All right, and then we also tried this. This is another approach where we use cellulose acetate, but using the phase inversions, we want it to be like a very thin film like this, okay? And it works really nice, okay, for the crystal violets, the mixed dyes of the crystal violets and the indigo coming. So this is still unpublished results yet, okay? And then this is one of those new works. Okay, we convert this OPFB, all palm empty fruit bunch, okay, into the CMC, okay, and we compare with the commercial one, so we can see the remarkable degradations of the methyl orange, okay, as well as the Congo rates for this particular study. And then you can see there will be a very good hydrophobic material here, okay? And we try also to involve the polymer conducting polymer, which is POPD, all right, for the photocatalytic degradations of the methyl orange, and can start to having a degradation as fast as 40 minutes, okay, right? So, and it depends, this hydrogel depends on the several parameters like the monomers, the pH, as well as the APS, the cross-linker, okay? And we can see the band gap of the bismuth ferrite as well, reduce, okay, from this. And it works towards the methyl orange reductions. Okay, then we moved into Offload Saxine. Okay, this is one of the antibiotic. We can see bismuth ferrite as well works well with the antibiotics, or we call it as a persistent organic pollutants. Okay, usually most of the metal oxides or semiconductor, it hurts to degrade the antibiotics. It needs like hydrogen peroxide and so on. So for our recent work, okay, we can see that it can work or degrade up to almost 75%, okay? And it's still undergoing. All right, so I think I covered everything from the control growth mechanisms up to the performance. Okay, so as a conclusions, we can see that many of the biopolymers still not investigated as a template agents for these inorganic phases, because most of these biopolymers or polysaccharides is owing a more complex behavior to be significant to control the growth of the metal oxide particles. Okay, so Therefore, it's not only a cheap and environmental friendly reagents, but it can be contribute to the valorizations of the renewable biological resource. So we hope that more depth of research in biotemplating, okay, for controlling growth, and perhaps that it will stimulate further research in these most fascinating of fields. All right. Okay. So by the way, this is USM. All right. This is our campus. Okay. This is near the bridge. We are in the island. Okay. So, and this is our QS World University rankings on 2020, 165. And I think I would thank you for this. All right. Thank you so much.
And thank you, Dr. Noor. And it was really a great elaborative presentation. We have some question from the audience, and, and Dr. Piyush Kumar Gupta, he has two questions to ask. So first thing he wants to ask is that what is the procedure to extract K carrageenan from the plant?
Okay. By the way, Dr. Piyush Kumar. Okay, thank you for the questions. By the way, we have a collaboration with this University Malaysia Sabah that they have a lot of seaweed from the isolations and also extraction part have been done from their universities, so that we just having that particular extractions or in a powder form when it comes to our lab.
Okay, Dr. Noor. And there is one more question from Dr. Piyush's side, and he also wants to know what will be the byproduct of the dye after the treatment with the BF4 nanoparticles.
Okay, that actually it depends on the types of dyes, but most of the basically that we can see, because there will be, I know that there will be a contradictions between just decolorizations or the degradations. Okay, but what can I say? Further mechanisms on the what particular intermediate that have been converted is not yet elucidate, but by using LCMS, we can see that, okay, also any mass spec, but we can also confirm that there will be a degradations percentage on the TOC. From the TOC results, we can see the degradations of the organic contents inside that. So most probably there will be a conversions into an intermediates before it can proceed into the water or carbon dioxide. But it's like a very quite long story, but because it's quite complicated, right, on the dyes or any phenols, but we have to check with the mass spec, or the most efficient one is the liquid chromatography mass spectroscopy. We work
Okay.
under it now.
Okay. Yeah. And there is one more question from Pushpendra Shukla, and he has a doubt that it was mentioned that the crystallite shape, it start changing from cubic to rod-like structure on increasing the annealing temperature from 550 to 600 and then 650 degrees centigrade. So is it happening for the same composition of the precursor, or there are some other
Yes,
parameter?
it's the same compositions of the precursor. If I can check here, it's for okay, it's still for molar ratio of 1 to 1.7, okay, most of it.
Okay. So thank you, Dr. Noor, and I hope our members were benefited with your presentation. Certainly, they would have, and I hope their queries are also answered. And thank you so much for taking your time out and sharing your work with all of us. And now I would like to invite our second speaker of the morning session. And our second speaker for this session is Dr. Whitley Corin Pau. and he is a senior research scientist at the Institute of Microelectronics Technology and High Purity Materials, Russia, and he will be delivering a talk on the characterization of nanoscale semiconducting materials by Raman spectroscopy. So before I invite Dr. Whitley to share his research work, I would like to give a brief introduction about him. And so his research interests include advanced low dimensional materials for application in microelectronics, Raman spectroscopy, signal processing, development of characterization techniques for nanoscale and disordered materials. And he has done his postdoc in the National Chiao Tung University and also at the Nano Carbon Research Institute, Japan. And he he has completed his graduation and post graduation from the Moscow State University, Department of Chemistry. Uh, and other than that, he is also reviewer of many international journals. To name a few: Applied Physics Letters, ACS Applied Energy Materials, Carbon, Scientific Reports, Surface Coat and Coating Technology, and many others. And also he has many research publications by his side. So with this brief introduction, I would like to invite Dr. Whitley to start his presentation and share his work with all of us. Sir, please.
Good morning, dear colleagues. First of all, thank you for your kind introduction. I hope you can hear me well. If not, please let me know.
Yes, your voice is properly audible and your screen is also visible here.
Thank you. So my talk is about Raman spectroscopy and especially about nanoscale Raman spectroscopy. I'm practically sure that it is not a good idea to remind Indian audience what is Raman spectroscopy, but I still will say a few words. So what we probe in Raman spectroscopy is the vibrational energy. So we shine the laser into the sample and we observe several different things. We observe luminescence, which is broadband, Raman stokes and Raman anti-stokes, which are shifted from the laser wavelength to the low energy and to the high energy respectively. What does it look like? You can see on this picture. And why can you be interested in Raman spectroscopy? For very wide spectrum of reasons. First of all, you can ask questions like, what kind of material is this? What are the concentrations of the components? What are the defects? And many other questions. No surprise that the Perseverance Mars rover, which is on Mars right now, has not only one, but actually two Raman spectrometers. This is very advanced and very, very efficient analytical instrument, which can give you a lot of very useful information about your samples. In this lecture, I would like to answer the question, is there anything special in nanoscale Raman spectroscopy, in spectroscopy of nanoscale materials? And actually, three main features of nanoscale materials are the size sensitivity of the Raman spectrum, asymmetric line shapes, which is in contrast to what we commonly observe in regular materials, and commonly faced problems to separate Raman spectrum from luminescence. Why this phenomena happens and how can we deal with it? This will be the main topic of my talk, and I will try to give you a couple of tools how to quantitatively analyze the Raman spectrum. So about the size sensitivity, I hope you can see on this picture that the Raman spectra of nanodiamonds have very pronounced size dependence. So here you can see bulk 42, 23, 4, and 3 nanometers. And how do we analyze the Raman spectra of nanoscale materials? When we deal with regular materials like, say, crystals or molecules, we usually have very well-established models. For example, crystals are analyzed in terms of phonons, and molecules have normal modes, and both of these things can be easily calculated with quantum chemistry and easily interpreted. In nanoscale materials, situation is something intermediate between the phonons, delocalized phonons, and the normal modes, which are very tightly localized. So how can we describe this thing? This is a very interesting question. How can we analyze them quantitatively? So before I start this, I would like to remind you that crystals have a ideally infinite number of atoms, and actually a number of phonon modes in crystals is infinite. It is something very different from what we have in molecules. In molecules, we have something like 3 multiplied by number of atoms minus 6 normal modes. So very small number of normal modes, very small number of vibrations. And each of these vibrations can be easily analyzed. In crystals, it is something very, very different. The number of normal modes is infinite. And how can we analyze them? Probably those of you who have a strong background in physics know it already very well, but for a general audience, I would give a brief reminder. How does it happen? So there are selection rules in Raman spectra for phonons, and the selection rules are like this. When we have all lattice cells vibrating in the same phase synchronously, like on this left figure 438 in Zinc Raman spectrum, this phonon, all lattice cells vibrate in the same phase. This phonon is allowed, but if there is some phase shift in vibrations between the neighboring two cells, then this kind of vibrations is forbidden. So most of the vibrations, actually almost all of them, are forbidden in Raman spectra for crystals. Only small number we can observe. Only zone center phonons, and this is actually very helpful. Otherwise, we would see something like continuous spectrum. The way we describe the vibrations in crystals is by the phase shift. This wave vector, and the meaning of this wave vector is actually this phase shift. It is something like 3-dimensional vector, which describes the magnitude and the direction of this phase shift. So you see here on this page, one phonon is allowed and another is forbidden. And coming to the way how we describe the phonons in nanoscale materials, in this figure, in these 3 figures, actually, we have the same thing. It is the same phenomenon displayed from 3 different points of view. We have phonon dispersion in the bottom, calculated and experimental. So phonon dispersion is the dependence of the phonon energy on this phase shift. And this is 3-dimensional, and the way physicists usually plot it is something like cross-section along high symmetry directions. This is what we have in the bottom. And depending on this phase shift, so for crystals, you can see here the gamma point on the bottom page, gamma point, and for crystals only the phonons with 0 wave vector are observed, and this means only 1 point here for diamond. This is 1333 inverse centimeters. So in Raman spectra of bulk crystal, we have only one narrow line, 333. But when we confine the crystal, we have some loosening or some relaxation of the selection rules. And one of the models, one of very efficient models how to describe this is that we consider vibrations of a big crystal, infinite crystal, and we localize them. We impose some localization function which actually represents your nanoparticle. We multiply the wave function of the localized phonon by this function, and we analyze this localized vibration. Then we decompose it to the basis of the original infinite wave function and see how the original phonon with near zero phase shift, how it is decomposed, how it is spread upon confinement. So on the next page, the general idea is that, as usual in Raman spectra, we represent, we deal with a Lorentzian-like line shape, and for each wave vector, we consider this Lorentzian-like shape which is on the top equation. In crystals, what we see is only one narrow line and only one Lorentzian from zero wave vector can be allowed. But when we localize phonon, it is spread along the Brillouin zone, along the space of these wave vectors. And depending on the localization, the tighter the localization, the more it is, the more relaxed is the selection rule. And the simple idea is to calculate this spreading just by decomposition of regional zone center phonon over the space of over the basis of all crystal wave functions. From this, we can actually give we can actually get a model which is quite easy to calculate. And in practice, until recent, what researchers did was to deal with, was to impose some approximation that would simplify this model, especially on the phonon dispersion. So the wave vector is a three-dimensional thing. It is phase shift. It of course can be 3 dimensions because the crystal is 3-dimensional. But for simplicity of calculations, until recent, what people did was to get some 1-dimensional function and put it in these integrals over the wave vector. And actually, this worked not very good, because for some crystals and even for diamond, the phonon dispersion is very strongly anisotropic. So it even can go to different sides, to different sides of energy. In one direction it is positive, and in another direction it is negative. So of course this should not work well if you try to build a consistent description. And in practice, recently quantum chemical calculations became available, and you can calculate what is the energy of the phonon depending on this phase shift on this wave vector. And you can compare this with experimental data, and actually you can get very good description of 3-dimensional phonon dispersion with quantum chemical calculations. And when you use this kind of data as input for the phonon confinement model, you can get very good description. How does it work in practice? So in this page, you can see calculated Raman spectra for diamond nanoparticles, which, as you can see, show quite obvious size dependence. This can be compared to experimental data, and actually this was done in several works. One useful thing which you can get from this is an instrument to analyze the Raman spectra of nanoparticles, and especially nanodiamonds. Nanodiamonds are very important applied materials, and the chemistry and technology and physics of nanodiamonds is developing very fast. So this is very useful for industry and for technology. So how to analyze the nanodiamonds, in terms of particle size, in terms of other things. So in this picture, you can see that we can first describe the phonon, the diamond phonon, localized diamond phonon. It is this line, subtracted from the experimental spectrum. And then we can quantitatively analyze after this the fraction of amorphous sp3 carbon and graphene-like carbon. So here GLC, graphene-like carbon, it is the surface layer because diamond surface in nanodiamonds it spontaneously reconstructs in sp2 in graphene-like carbon. So it also has a very strong feature in Raman spectrum, especially for small size nanodiamonds. And in the bottom curve, you can see the calculated thing, which confirms the assignment of 1250 band to amorphous sp3 carbon. So this is very efficient tool to analyze the Raman spectra of small sp3 carbon materials. When it comes to different materials, only recently it became possible to apply this kind of phonon confinement model to more complex materials with complex Raman spectra, like zinc oxide. It has several bands. So in this picture, you see experimental spectra for different size, and these experimental spectra show very clear size dependence, especially in the low frequency region. In this low frequency region, we can see so-called localized acoustic phonons, which is a very interesting thing, and which was until recent impossible to analyze with in terms of phonon confinement. Only with the quantum chemical calculations, after they were implemented in the phonon confinement model, this became possible. So how it looks when we compare the experimental spectra with the calculated data, it is in this page. So we have low wave number region and high wave number region, two regions. And this kind of size dependence, especially in low wave number region, localized acoustic phonons, it is actually very well reproduced by the calculations. In high wave number region for zinc oxide is very special, and it cannot be analyzed. This strong band cannot be analyzed with a phonon confinement model very well, because it is symmetric even for the bulk crystal. There is some phonon interaction, which makes the shape of this band, experimental shape, asymmetric, and it is skewed towards the low wave number. So this is very special for zinc oxide. But for the low wave number region, the calculated phonon spectrum, localized phonon spectrum, matches the experimental data on nanoparticles very well. And one more thing which we can apply this kind of model is the disordered networks. It is not exactly nanoparticles. It is something like localized vibrations in this case in silica, in vitro silica, infused silica. We can analyze the Raman spectrum, experimental Raman spectrum, in terms of what kind of localized modes can be there, and can we interpret the Raman spectrum? Can we analyze it in terms of something like characteristic localization length, localization scale of the phonons? And when we compare calculated and experimental Raman spectra, we can see that the best match between experiment and calculated is for this something like 1 nanometer vibrations, which can be represented with the cluster, which is shown here in red on the right side. And the last very interesting thing about the phonon confinement is that we can try to analyze not only solids, not only nanoparticles, but we can also apply it to liquid, which is very special. So in this page, you can see experimental data. And these experimental data are the decomposition of a big data set obtained at different temperatures. So there are several hundred of Raman spectra obtained at different temperatures, which were decomposed into the independent components, which are observed at different temperatures. So in this figure B, you can see temperature dependence of the components which are in the A. And it is actually very well known that for that ordinary room temperature water is a combination of two structural components. One of them is more ordered than the other is less ordered. What is more special is that at low temperatures, especially in supercooled water, we can observe the third component, and this third component is something what we can call a liquid nano ice. It is very small, but still liquid, but very ordered structure in water, which gives a characteristic Raman spectral pattern, which is here in green. And the question we can ask whether we can calculate what is the size of this ordered component, what is the something like phonon propagation scale. And when we compare the calculated and experimental spectra for different size, this is what we have in this page. So on the top is the ice. This is the crystal. This is the infinite crystal, experimental in the top and calculated with the dotted lines. Next one is C. This is the liquid nano ice. And the best agreement between experiment and calculated is for the like 2 to 4 nanometers clusters. Then the next one is less ordered water, and the bottom one cannot be reproduced with this kind of calculations because this is completely disordered phase. And on the right side, you can see the characteristic size of the cluster and how does this cluster look like if we build it with water molecules. So this kind of cluster, ordered liquid nano ice cluster, exists in water, especially in supercooled water, but it can be observed below 10 degrees C. So this is all about the phonons and localized phonons in Raman spectra. And now let me move to the baseline. Baseline is in Raman spectra is very important, and the common origin of this baseline is the luminescence, which is something like electronic excitation. The question is whether we can efficiently and consistently separate the vibrational, or in other words, Raman signal from the electronic or luminescence. How can we do this efficiently and consistently? Actually, this is a very important question, and it is under active development right now. And there are several generations of approaches how to do this algorithmically. And most of modern algorithms work very well with well-separated lines and the lines which are sharp and have no tails. But when there are overlapped lines, and when we have pronounced tails, like in this figure, then this is actually a strong problem for most of modern algorithms. Let me show you on the next page. So this is the test of algorithms, of several modern algorithms, including morphological wavelets and some asymmetrical least squares. And this is how they agree with the experimental data. And you can see that most of them really have difficulties with this kind of spectra, which have broad bands and especially superimposed bands and pronounced tails. So whether we can build an algorithm which would deal with this kind of spectra efficiently, and whether we can quantitatively estimate the performance of the algorithms, this is what I would like to tell a few words about. So one idea how to distinguish the luminescence and Raman peaks is that we can hypothesize that near the peaks, the derivatives, both first and second derivatives of the spectra, strongly deviate from the average values. And on the plot B, you can see that this black curve is the second derivative of the experimental, of the smoothed experimental spectrum, and we can indeed see that it has very pronounced features near the peaks, and near the peaks it deviates from the average values very significantly. It does not work with the raw experimental spectra because it has some noise, and if we try to do it with the raw experimental spectra, we just get this gray noisy line. But so we need to apply some kind of smoothing, or it can be also called mollification. If we do it, then we can see that the peaks can be detected very well just by their derivatives. Next, based on these derivatives, we can build a screening function, some function which is the main idea of which is just the deviation, the quantification of this deviation from mean values of the first and second derivatives. And this is plotted on the third page. This is just the screening function, which the main purpose of which is to detect the peaks. And as you can see, if you compare it to the top plot, it really does detect the peaks in the Raman spectra. So this screening is a tool to detect the peaks, and this screening is can be applied to advanced algorithms as one of the tools to help them to separate the baseline from the peaks. And one of the most efficient algorithms is asymmetric least squares approach. And there are three basic things in this algorithm. So the baseline, we search the baseline as a smooth curve, and we do not try to impose any analytical shape, like for example, in polynomials or in spline approaches. So in this algorithm, we do not impose any analytical shape on this curve, and we are searching for the baseline, which is not above the experimental data, which is natural. So in terms of equations, it means that we can weight. We can apply some kind of weighting to the difference between calculated baseline and experimental data. And the final thing is that the baseline needs to be smooth. And the quantitative thing to do this smoothing is just penalizing the second derivative of the baseline by some kind of parameter lambda, which is noted here as lambda. And these three ideas can be put into one simple equation, which is the main idea of asymmetric least squares algorithms, of the big family of this kind of algorithms. And and the main idea is to minimize the functional f, which is here in the center. So coming back to the weighting and the peak detection, if we apply this kind of screening to the weights in this kind of algorithms, we can get good descriptions of overlapping peaks and long tails. How does it work in practice? So in this picture on the right, the black dashed curve is the algorithm which I just described. So we use asymmetric least squares and penalize the second derivatives, and we screen the second derivatives of the peaks. And if we compare how does it perform to the other modern algorithms, we can see that it actually gives a very good and very consistent description of the baseline. And on the left side, this is the performance of several baseline algorithms, and in this plot, the smaller is the better. So deviation here is defined on a synthetic data set for which the baseline and the peaks are known. So it is the big data set, about 1,000 spectra, composed of the known baselines and known peaks. And the idea is we feed this data set to different algorithms, and we check how does the algorithm reproduce the already known to us, this baseline, and we calculate the deviation between the calculated and the known baseline. So we can see that this algorithm, which is based on the screening and penalizing the second derivatives, it works very efficiently. Very good thing about this algorithm that it has a Python code, Python script, which is available on GitHub. So actually, if you are interested, you can try all these algorithms which are here. You can try them by yourself on your Raman Spectra. It is actually very simple. So link is in this JRS, Journal of Raman Spectroscopy, in this paper, and its supplementary information. So you can try this algorithm by yourself. It is very efficient and very useful tool to analyze the Raman spectrum. Another tool is asymmetric lines. So we are used to the fact that line shapes in Raman and the infrared and many other spectra are symmetric, and that we can analyze them like Lorentzian, Gaussian, or their combination, which is usually called Vogt function. But the fact is that in nanoscale materials, and actually not only in nanoscale materials, in a wide range of materials, the lines are asymmetric. And there are many attempts to build the symmetric function, which would describe the line shape efficiently. Some of these functions are based on the models, on the physical models of, like, say, Phonon resonance line. But for many cases, the origin of the symmetry is not known, or maybe it can have multiple origins. And the question is whether we can formulate such function that would be flexible and would give a good description regardless of the physical reason of the origin of this asymmetry. And if we, so in mathematics, if we apply a symmetric perturbation to the symmetric function, and this perturbation should be damped on the top curve here. So this is the damped perturbation. Damped here means that it converges to zero on the tails, and it is very important because if it does not converge to zero, then the integral of your line would be diverging, and it is actually a common problem of many approaches that they give diverging integral. And if you have a diverging integral, then consistently extract the integral intensity from your line would be a real problem. So here it is damped perturbation, and when it is damped, you can apply it to your x-axis and get a very good asymmetric line, which is very flexible, and which when we use it to experimental spectra can describe a wide variety of line shapes. So coming to the comparison with the experiment, here you see several spectra. Actually, there are many of spectra tested, but several very important examples are here. I mentioned already zinc oxide when I talked about the phonons in it. In zinc oxide, we have a symmetric line 438. And on the left, you can see how this line is described with asymmetric functions, and on the right with symmetric functions. You can see that much better, of course, with the asymmetric functions. And in graphene, in highly oriented pyrolytic graphite, there is a second order band which is also asymmetric, and you can also see that it is much better described the asymmetric function than the symmetric. In spectra of nanodiamonds, you can also very efficiently analyze it with asymmetric functions much better than the symmetric. And the same in polymers. In polymers, it is very common phenomena that the lines are asymmetric because there is some degree of disorder. And in PTFE, in Teflon, one of the lines is asymmetric, and as you can see, it is much better described with the line shape, which I just mentioned. So, dear colleagues, that would be the final page of my talk. So I would like to mention my teacher, Professor Hamaguchi, which is professor from Tokyo University, and he used to say to his students that what matters is not your spectrometer, but what you do with it and with your data. Probably if you just start working with the Raman spectroscopy, or you don't have much experience, and even probably if you do have good experience, you still would have a lot of questions like why I don't have a good signal from my sample, how do I deconvolute spectra into components, how do I analyze big data sets, how to process Raman maps and make nice figures, what is a reliable way to extract this such and such parameter from my spectra, and so on and so on. Actually, there are a lot of questions which spectroscopists face many times, no matter what is their experience. A short way is, of course, to ask experienced colleague, and if you don't have this kind of colleague, you have to read papers, try and learn. And what I hope is that with my talk, I gave you some instruments which I hope would be of some use to you, and which can be a good starting point to analyze the spectra. Please let me know if this talk was interesting to you and if it was useful. So thank you. This is it.
Thank you so much, sir. And you have very rightly mentioned at the end that whenever you work with the spectroscopic data, so especially if it is a new material, you will end up having many doubts that whether I'm getting the correct data or not. Is it really from the sample or from the impurities? How to analyze it? So yeah, you have very rightly mentioned all the points, and indeed it was a good presentation. And you also in the beginning, the point which you mentioned, that it is much easier to deal with the molecular Raman spectroscopy because of relatively less number of vibrational modes associated there, but it is not that simple in case of crystals. So it was a good presentation, certainly. And the floor is open now for the questions. So anybody have any questions, please feel free, and you can ask your questions to Dr. Whitley here. I do not see any questions in the chat box as of now. Maybe it was very well elaborative. So maybe people do not have any specific question as of now. But I was really benefited. I can certainly speak for myself that it was a good presentation.
Thank you very much.
Yeah, and hopefully we'll stay connected for some of the Raman spectroscopy related data analysis and discussions.
Thank you.
Yeah, thank you so much, sir. And since we do not have any questions here, so I would like to announce the end of our morning session of this day 2 of 1 week long faculty development program on quality engineering and technological advances in materials and devices. And I hope to see you all again in the evening session, which will be starting at 3 p.m. And so